Hey everybody, welcome to the third video on square roots and Pythagorean theorem, and we're going to be comparing squares and roots today. We're going to be talking about what it means to be a square and what it means to be a root, and not the square like the lame person, the square more like the geometric shape, but also the algebraic expression that represents that geometric shape. Did I just say a whole lot of math words all at once and confuse you? I probably did. But that's okay. You're going to see it in practice right here. Let's get started. Okay. So first of all, I have a little diagram here with two questions. So first one is, what is a square and what is the root of a square? Now, what is a square? Yeah, you're thinking, well, duh, there's one right here. And well, actually, there's a whole lot of squares there's even a really big square, and there's squares inside of squares. Like, there's squares everywhere. Those are all squares. Yeah, they are squares. So yes, I know you can identify what a geometric shape called a square is, right? This is a square right here. Yes, but in algebra, in the stuff that we're doing now with math, you also need to know that a square is something like that, where you have two of the same number multiplied together. So 2 squared is equal to 2 times 2, right? That's a square when I have the same number multiplied by itself. We're going to come back to that and you'll understand why that is important in a second. All right? And here we go with the second question. What is the root of a square? So if a square is this, and if I asked you the question, I know you'd get it, but if I asked you the question that I had side lengths of 2 and 2, you should be able to tell me that the area is 4. 2 squared is 4. Okay? So a square of a number gives me the area. And if I do the reverse, which is really what a root is, it's the reverse of a square, the opposite direction of a square. If I had 4, the root of a square is really the pieces that make up the square. So the root of this one is the side lengths, 2 and 2. So think of it like going in reverse in a way. So 4. Let's look at this 4 again. So 4, in the last video we talked about prime factorization and breaking something up, right? If we use the tree method, we could break up 4 into 2 and 2. Sure. And we know that this is 2 times 2 is 4. We also know that 2 times 2 is the same thing as 2 squared. Hint, hint. This right here, this bit underneath, that is the root bit. All right? So it's the thing that's being squared. It's the side right here that is going to give us the area. Okay? Let's try it just like looking at it a little bit. All right? So here we have an example of a square. Side length of 1 times 1. Here's another one. 2 times 2 gives us 4 blocks in the middle. How about this one? 3 blocks times 3 blocks gives us 9 blocks. You notice how all the sides remain the same all the way through. And what ends up happening all the way over here, all the way up to, nice that worked out perfectly. We have, how many blocks is that? 20? I don't even know. 2, 4, 6, yeah, it's got to be 20 blocks. So 20 times 20, if I had a side length of 20, and this is a perfect square, then my area, without even needing to count all the blocks, I mean, I could, but that'd be a waste of my time and a waste of your time, would just be 20 squared, or 20 times 20. So there are actually 400 blocks inside of here. Okay? You know, I should have asked you, like, can you tell me how many squares are in here? Right? That would have been a good way to start the video. Maybe I should re-record it. No, it's a little late. Maybe I won't do that. But you should be able to figure that out. Okay, here's a quick question. Prime factorize 900 to find the square root of the number. Now, we did prime factorization in the last video, so if you don't remember how to do that, you should definitely go back and learn that because it's super important. There were two methods. There was the factor tree method, and there was the divisor, or the dividing, whatever you want to call it, the dividing method. Doesn't matter which one we do. I like the tree method, so I'm going to go with that. I'm going to start off with my number of 900, and I'm already looking at that, and I know because of zeros that I can multiply it, or I can break it down into 10, 100. So I can actually break that down into 100 times 9. Okay? I could do that, or I could do 10 times 90, or I don't know. There's a lot of different options here. Let's start with the 100 side here. So 100 can be broken down into 10 and 10, which further breaks down to 2 and 5, 2 and 5. My 9 over here, why did I write an A? Because I'm tired. My 9 breaks down to 3 and 3. So just looking at all the circles here, there are no unended branches. So my 900 is actually equal to 2 times 2 times 3 times 3 times 5 times 5. And let me just confirm that here on the calculator in case you don't believe me. 2 times 2 times 3 times 3 times 5 times 5 gives me 900. Okay. So, what we did here is we broke it down into the primes. And the important thing that I want to point out is that they're all in sets of 2. So that's really important here. So another way I could write this is 900 is equal to 2 squared times 3 squared times 5 squared. That's going to be useful later on when we're dealing with how to solve square roots. Okay, so remember that when you have a set of 2, like 2 times 2, that's 2 squared. 3 times 3, 3 squared. Okay? So did we answer the question? We prime factorize to find the square root of the number. Oh, we're supposed to find the square root of the number. So I am telling you of something we're going to use in the future, and we're already using it now. So if we have square root of 900, and we said that 900 is 2 times 2 times 3 times 3 times 5 times 5, well, then the square root is also. So the square root is 2 times 2, sorry for my bad writing, times 3 times 3 times 5 times 5, which I also said, here's where it's interesting, 2 squared times 3 squared times 5 squared, because they're sets of 2, right? Because this turns into that, this turns into that, and this turns into that. So the beautiful thing here is that a square and a square root are opposite operations. Just like if, remember before I said 4 is equal to 2 squared? I said 4 is equal to 2 squared. Well, the square root of 4 is equal to the square root of 2 squared. I could also point out here that 4 is equal to the square root of 4 squared, right? Because these will cancel out. And remember, 4 squared is 16. So the square where there's an area of 16 would have sides of 4. Okay? I know that's kind of tricky, but let's look at it in practice. So here, what you need to realize is that this square is going to cancel out with its part of the square root, so it's going to come on the outside of the square root. So because I got rid of that square, this now exits the square root. And we can get rid of this square, so this 3 exits the square root. And we can get rid of this square, so this one exits the square root. So what we have is square root of 900 is equal to 2 times 3 times 5. And yes, technically the square root is still there, but the only thing left is really a 1, the square root of 1, because, you know, multiply anything by 1 and it's 1. So the square root of 1 is just 1. So that is gone, really. So in the end, all we did is got rid of the ones that have squares, took them outside, and whatever didn't, we would have to leave under the square root. But you're not going to have to deal with ones that are having little bits left inside the square root. Not until later. That's probably like 10th grade that you're going to have to worry about that. Maybe 9th grade. I don't know. So what we have now is that the square root of the number 900 is 2 times 3 times 5. Now, can I solve that? Well, 2 times 3 is 6. 6 times 5 is 30. So we have a big, ugly number like 900, and even without a calculator, we've used prime factorization to break it down to 30. Okay? All right, that was a long one. There's not too much left. This is a short video. I promise we're just about done. So step 1, prime factorize the following numbers. Step 2, demonstrate a no calculator technique. Step 3, find the side length. All right, so we can use any method here. Let's use the divisor method. So we got 576, and let's divide that. So 576, let's divide it by 2. That's 288. Oh, I did it in the other direction, right? I'm supposed to write it the other way. That's why I don't even use this method very much. All right, 2, and that's 288. All right, now I can definitely divide by 2 again, so let's do that one by 2, and we get 144. Ooh, I like 144. That is a perfect square. All right, so 2 again, and that's 72 here. We can divide 72 by 2 again, and we are going to get 36. And you can kind of see where I'm going with this. Then we get rid of 2 again, and we are down to 18. Whoops, I changed that. 18. And then we can break the 18 down to 9, and then to 3, and then to 3, and we have a whole lot of numbers here. These are the ones that matter. So let's look at the sets of 2. We've got 2 squared, 2 squared, 2 squared, and 3 squared. So if I looked at this and I said I'm looking to do the square root, then I'm actually able to write 2 squared times 2 squared times 2 squared times 3 squared. And remember that anything with a square will cancel out, and it'll come out of the square root. So I'm left with 2 times 2 times 2 times 3, which is 2 times 2 is 4. 4 times 2 is now 8. And 8 times 3 is 24. So the square root of 576 is 24. Not bad. How about 441? Let's try a factor tree here. 441 divided by 3. Okay. 3 is prime, so let's go with 147. 147, what can I divide that by? Maybe 7. Yep. 7 is prime, and I'm left with 21. 21 can be divided by 3. So 3 and 7. And 7 is prime. So what we're left with is, remember, 3 times 3 times 7 times 7. And I'm looking at sets of 2. So that is, remember, this is all square root. 3 squared times 7. Whoops, what did I do that for? Oh no. Times 7 squared. Anything squared is going to get canceled out and come outside. So I'm left with 3 times 7, which is 21. So the square root of 441 is equal to 21. I can check that on my calculator. Yes, I know it is easy to go 441 and just do the square root and get a number, but that's not the point, because you're going to have to be able to do it without a calculator. And there is a no calculator portion of the exam that you're going to have to take next year. So you do need to know this stuff. Don't just cheese your way through. Learn it the proper way. Okay. And now we're right at the end here. You need to try this out by yourself. So you have square root of 676, square root of 625. Give that a shot. See if you get the same answers as I do. Go ahead and pause the video. And what I get here is I used the dividing method here, and I broke it down 676 to 338 to 169. Then I got stumped, and I'm like, oh yeah, 13. And then I broke it down further. And so then when I got out of these numbers, I put them under the square root, and I realized I had sets of 2, 2 times 2, and 13 times 13, which could come out because they are squares, and they cancel with the square root. And then I get 2 times 13 is 26. On the other side, I used the factor tree, broke it down. I saw it was a 625, and anything 25, 50, 75, I know can be broken down by 25. So I did 25, and hey, 25. Those break down to 5, 5, 5, 5, which you have 2 sets of 5 squared, and that ends up being 25. And that's what you should have gotten as well. Last thing that we do here is we are using prime factorization to prove why 9 times 25 equals 16, why that is equal to the other thing. And there's a couple different ways we can do it. The simplest way is probably just to break them down to show that the components are the same. Because if the components are the same, then they are the same. So I look at this 9. I'm going to break down 9 into its pieces, which is 3 times 3. I'm going to break down the 25 into its pieces, which is 5 times 5. 16 is 2 times 8, which is 2 times 4, which is 2 times 2. So my pieces for the 9, 25, 16 are... what did I write here? There's a 5. Okay, so I have 2, 2, 2, 2. So I have 2 times 2 times 2 times 2 times 3, 3 times 5 times 5. So that's what this one turned into. Now let's try this one, and we'll see if it's the same. Let's break down the pieces. 12 is the same as 3 times 4, which is 2, 2. 15 is 3 times 5. And 20 is 4 times 5. And the 4 breaks down to 2, 2. So let's count these out. I have 4 2's. 1, 2, 3, 4. Whoa, I didn't mean to write 4. I meant that there are 4 2's. And then I have a 3 and a 3. And I have a 5 and a 5. So just by breaking down the components, I can see that they match up identically. So the 9 times 25 times 16 is identical to the 12 times 15 times 20. I could have also solved them and gotten a number. There's a couple different ways I could prove that, but just by seeing it visually, you can already tell that they are the same just by breaking it down into its bits and pieces. And this is where we stop. We are done with this part.